Okay, hi. Finally ready to start class. We had been talking about mods in the class last time, but I sort of was confusing. So I was gonna go back to some of this and just to write some stuff on the board. Here's the handout again. But I was gonna write some of the definitions. And also I think one thing that can be helpful to do is to actually, we can make addition and multiplication tables for mods, and then you can sort of see the full structure of the mod from that. Like if you're in mod 5 or mod 7 or something. So yeah, let me just write stuff on the board. That's the right here, okay. So, there's actually like 3 equivalent definitions of mod. There's the one I gave on the board. Right, so let's talk about modular arithmetic a little more. So given A and B in the integers, we say A is congruent to B mod M if and only if, I'll give you 3 equivalent definitions. You could say, like on the screen there exists a K in the integers such that A equals B plus MK. So that idea was that we just like, they're off by a multiple of M from each other. Or you could say M divides A minus B. So the difference is a multiple of M. Or you could say, and we'll talk about division in a little bit, but A and B have the same remainder when you divide by M. Right, and so these are actually all equivalent definitions. They're not 3 separate pieces of definition. They're all equivalent to each other. Let me write that down. These are equivalent definitions. So just as an example, like something like I don't know, if we took 50, I claim that 50 is congruent to 76 mod 13. So the question is, do you believe that that fits any of these 3 definitions? Can I write? Are they off by a multiple of 13 from each other? Yeah, they're off by each other by 26, and yeah, so we could write 50 is 76 plus 13 times -2, I guess, right? Or 13 divides 50 minus 76. Doesn't really matter which order I do it in. It turns out it doesn't, A is congruent to B and B is congruent to A. Or let's see, 50 when we divide by 13 is 39 plus 11. The nearest, well, that's not the nearest multiple of 13, it's the biggest multiple of 13 less than 50. Yeah. Hello, hi, how's it going? No, Rachel is going to. So Mrs. Taverge actually gave me another keyboard. So this is the one over here that's broken.
Okay.
But she does want her keyboard. Mrs. Taverge wants her keyboard back. So if you have another one.
Sorry, I missed the window.
Yeah. No, that's totally fine.
Between classes here.
Let's see if this still.
Make sure it plays nice.
Yeah, it's doing all that
Yay.
stuff. Awesome.
So
That's the dead one, and I'll return this to Mrs. Taverge after class. Awesome. Thank you so much. Appreciate you running over. All right, thank you. Okay. Yeah, Professor Connolly was on the phone outside yelling at IT to get over. I appreciate that. Okay. Okay, so does this also work? 76, what multiple of 13? That's the biggest multiple of 13, less than 76. Fifth multiple, which is 65. 5 times 13 plus 11. So yeah, right? And if you reduce either of these, I guess the point is that that's the same remainder. If you reduce either of these, I talked about reducing mod 13. So you could say, if we reduce mod 13, they're both equivalent to 11. $50 is congruent to 11 mod 13. 76 is congruent to 11 mod 13. To reduce is to reduce it to a number between 0 and 12, right? Because those are the possible remainders when you divide by 13. Yeah. Though I also said a lot of times it's better to take the smallest number. And I could have used 4 times 13. And then what would my remainder have been? If I did 4 times 13. It'd be -2, right? Because it'd be 52 minus 2. So -2 could also work. It just depends on whether you want positive remainders or smallest remainders. And so notice sometimes it's more convenient to use smallest remainder, smallest sort of in size remainder instead of positive, or instead of non-negative remainder. So maybe you'd rather write that 50 is congruent to -2 mod 13. And again, you can check the difference is 52, and that's also 13, right? Or I can shift by 13s. There's another way I think about this stuff sometimes, which is that anytime I see a 13, I just really think of it as 0. Because 13 is congruent to 0 mod 13, right? All the multiples of 13 are 0 mod 13. And if your mind, if you just say, okay, every time I see a 13, I'm gonna treat it as 0, then this just goes away and you get 50 equals 11, right? Stuff like that. So sometimes that's useful, So mod 13 is like, so I guess I'll just say or, worth mentioning, like mod 13 is like the integers, but with the extra equation. Just depends on how you want to think about stuff. The extra equation 13 equals 0. Right? You're just sort of like throwing that, you're like adding that relationship into the integers. And all the consequences is that everything can be turned into a number between 0 and 12 if you do that. Make sense? Okay. So what I was going to say next is that you can actually make addition or multiplication tables, because we can think, like, if we want to think about, like, let's just think about mod 5 for a second. let's just go mod 5 for a second. We can think of this as the set, or we can think of the set 0, 1, 2, 3, 4 with addition and multiplication mod 5. So now, like, this set is now closed under those if you're always reducing mod 5. So actually, you can actually think of this as a completely different number system, like a new number system. Like sometimes people write, maybe I should just say, this is a new number system. We can do this for any mod. And there's different ways to write this. We can write this, there's different notations for this. So some notations. Some people just write Z sub 5 to represent that set with that definition of addition multiplication. If you go on and take abstract algebra, you'll write it this way. If you go and take like the rings and fields class, some people write Z mod 5Z. Kind of a weird. Kind of a little bit of a weird notation. You can think of 5Z as the multiples of 5. Like I could write 5Z to represent the multiples of 5, all the integers, you know, because you're just taking everything in Z, multiplying it by 5. And so modding, there's actually a real sense in which it's like a quotienting, like you're sort of, like it's like adding this 5 equal, like anything in here, you're just gonna turn into 0. So you're just like dividing out all this stuff to make them all 0. And then you're left, that's what you're left with. But I'll say a little bit more about that at some point because I actually will give a formal construction of this once we know about equivalence relations. But yeah, like we can really think about these things as their own number systems. And so then you can make addition and multiplication tables. Like you can make the addition table for this, which is not super exciting. The multiplication tables are more interesting, but 0, 1, 2, 3, 4 this way, 0, 1, 2, 3, 4 this way. And you can add, okay, so 0 plus everything is itself. That's not very interesting. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. What's 4 plus 1? What's 5 really? Everything is equal to something in this set. What's 5 mod 5? 0. So 4 plus 1 is 0. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3, 0. 2 plus 4 is 6, which is 1. 3 plus 1 is 4. 3 plus 2 is 5, which is 0. 3 plus 3 is 6, which is 1. 3 plus 4 is 7, which is 2. And so on, right? 1, 2, 3. Wait, what am I doing? Oh no, I miswrote. I was like just gonna keep the pattern going, but 4, 0, 1, 2, 3. So that's the addition table, mod 5. Right, like C5 up here or something like that. Does that make sense what we're doing? We're just, every time we get above the mod, we're just reducing down. And we can do the same thing. We can make a multiplication table also, right? Okay. I'm not making these long enough. Okay, so actually when you make multiplication tables, you often don't include this first column or first row because they're kind of boring. You sometimes just don't include the 0. Even this next row is kind of boring, right? But now you can fill in the rest, right? 2 times 2 is 4. What's 2 times 3? 1. 2 times 3 is 6, which is 1. 2 times 4 is 8, which is 3. Well, these tables are actually symmetric, I guess, across the like diagonal, right? 3 times 2 is 4. 3, 2, 2. 4 times 4 is 16, which is 1. That's one of those places where it might even be easier to think of this as like -1. Because -1 times -1 is 1. Okay, so you can do this. You can do this for different mods, and there's actually a lot of interesting structure here. Let's actually do like the mod 6 multiplication table. And I'm actually going to ask you guys to go and put a few more on the boards, just so we can look at the structure. I claim there's some interesting structure in some of these. But yeah, let's do the mod 6 one here. I'm going to leave out the 0. Like a lot of times people leave out these because that's kind of a little bit boring. So mod 6. 2, 3, 4. Actually, that's it. 1, 2, 3, 4, 5. 1, 2, 3, 4. Take a minute and fill this in. Let me check with your neighbors and see. Yeah, okay, let's just not include the 0. Do the easy part. The addition tables are kind of boring. We don't usually write those down very much. You can sort of see what the addition table is going to look like. Always, we do mainly, the multiplication tables are much more interesting. Now you're doing mod 6, right? So what did you get for the second row? The second row. 24024. Yeah, 2 times 3 is 6, which is 0. 2 times 4 is 2, is 10, is 8, which is 2. 2 times 5 is 10, which is 4. What about the next row? Yeah, right. It's kind of goofy. You get some weird patterns here. 3 times 2 is 6. 3 times 3 is 9, which is 3. 3 times 4 is 12, which is 0. 3 times 5 is 15, which is 3 more than 12. This is 42042. And then what's the last row? Someone see the last row. 54321. Yeah. 5 times 2 is 10, which is 4. 5 times 3 is 15, which is 3. 5 times 4 is 20, which is 2 more than 18. 5 times 5 is 25, which is 1 more than 24. You could also think of this as -1, so it's like -1, -2, -3, -4, -5. Yeah. Okay. I just want to call attention to one thing immediately, which is these zeros, right? You can now multiply two things and get 0, two things that are not 0 themselves and get 0. That's surprising. That's not something we're used to in the integers, right? Taking two non-zero numbers and multiplying them to get 0. And there are certainly differences between these two tables. This is mod 5, and that one's mod 6. Yeah, let's actually do. How many groups would we be in if when we do groups? How many groups do we make? Do we make 5 groups? Make somebody do the mod 11 multiplication table. Who feels like they're going to be good at this? Wait, so what are the groups when we do groups? Like, who's you two? With someone else? Just you two. People are missing today too. 2, 4, 6, 8, 10, 11. I don't know who's. There's like at least 3 people missing. Yeah, because you're like by yourself, right? Yeah, let's I can't remember how the groups work. I'm sorry. Like, so let's go to the boards as we would, and I'll put Kevin with someone with another group, just so I can see the groups, and then I'll tell you guys which multiplication table to make. Yeah, Kevin, maybe you can, or actually, do you want to join, Kevin? Yeah. Okay, so you guys do the mod 7 multiplication table. Remember, you can leave out the 0. You do the mod 8. You do the mod 9, mod 10, and mod 11. Remember, you don't have to fill out like an upper triangle. You can always reflect across. And you can leave out the 0. I'll pause the recording and. Recording. Look at this. Look at this work. Look at this work my students are doing. Recorded for posterity. Mod 11 is getting unpleasant, huh? No, oh, you're just not making horizontal lines. Here's the mod 7 table. Ooh, there's an interesting pattern. Some sort of diamond pattern in the mod 8 table. Yeah, no, 8.8. Wait, you guys finished at 9? This is the Z9 table. Maybe I should take photos of these two, but this is the Z10 table. I'm recording again, so I wanted to keep this all on camera. Interesting. Now let's see if we can get the Z11 table or if it's cut off. Or... Oh no. Didn't quite work. Well, we got most of it. You could reconstruct the rest of it because of the diagonal symmetry, right? And I like those lines at the bottom there. Okay, so yeah, there you go. I'll try to take photos of those. Let me go back to the board. But in general, there's some patterns, right? So what are some of the patterns that we're noticing? Yeah, what are some of the patterns that we're noticing in these tables? I saw, yeah, audio. So like in the one you were doing, Mod 11. So 11 is prime, and you notice that every number was appearing. Over here, look at it again. That in a given row or column, so we'll focus on columns here, that you're getting every number exactly once. So obviously 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, but 1, 2, is that a 3? 4, 5, 6, 7, 8, 9, 10. Yeah, it looks like, so you're saying 11's prime and somehow you're getting every number. Okay, what about, and what's the other one? Mod 7, I guess, is the other one that would be true for. That's the other prime that we did. Ooh. Turn camera. Oh, that also true that every number appears once, and it's like a Sudoku kind of. Every number appears exactly once in every row and column. But then when you go to like 8 or 9 or 10, what happens now? So you guys were noticing those zeros, right? Diagonal. Well, there's this nice pattern with the 4, 4, 4, 4, 0, 0, 0. That's nice. What about, so in this row, all the numbers appear. In this row, you only get 0, 2, 4, 6. In this row, you get 1 through 7. In this row, you just get 0 and 4. In this row, you get 1 through 7. 0, 2, 4, 6. 1 through 7. That's interesting. Something going on here. 9. Is there something similar with 9? No. First shot. Okay. So what happens with the 9, the rows? Here you get all the numbers 1 through 8. You get all the numbers 1 through 8 here. Here, no, just 0, 3, and 6. Here, yes, all the numbers 1 through 8. Here, yes, all the numbers 1 through 8. Here, just 0, 3, and 6. Here, all the numbers 1 through 8. Here, all the numbers 1 through 8. Interesting. And like, let's just look at 10 to complete the. What happens in this one? Something similar? The 5 row is particularly interesting, right? You just get 0s and 5s. The 2, 4, 6, and 8 rows all have 2, 4, 6, and 8 and 0. And the 1, 3, 7, and 9 rows have all the numbers. Okay, so what's going on? What's that? Life? Is that what you said? Yeah. Go back to the board. Yeah, what is going on here? So there is something interesting going on. So let me define 2 different terms for you guys that I think are relevant terminology. Let me get this recentered again. Okay, so here's some terminology. In a number system, so actually these things, all of these Z mod N, Z mod M are rings. They satisfy those ring axioms. Maybe I should say that first. Z mod M are all rings. They satisfy axioms 0 through 5, 0 through 6 from our axiom sheet. Our axiom sheet. So what, namely, plus and times are closed operations, meaning they're like, I think that's what axiom 0 was. Like closure is like, is the operation well defined? If you add 2 things in the set, you get something in this set. If you multiply 2 things in the set, you get something in the set. Closed, they're commutative, associative, times distributes over plus. You can check all these, like these are still true. And you have an additive and multiplicative identities. 0 and 1 still work. And you also have additive inverses still, right? We talked about sort of, I mean, here it's a little bit interesting, right? Like, I guess just for the addition table up there, like 2 and 3 are additive inverses mod 5. Right? Like there is a sense of -2 mod 5, it's 3. So this is true, this is true, this is true, this is true. So this, for example, 2 plus 3 is 0 mod 5. So 3 is really what -2 is mod 5, right? Etc. So everything has an additive inverse. That's what I said. It satisfies all those axioms. So they are rings, which is nice. Like when you take the rings in field class, these are like an important class of examples you'll end up studying. But let me give you 2 definitions of terms that exist in all sort of rings. So some terminology. Does this make sense about the additive inverses thing? Terminology. So definition. I'm just going to say let R be a ring. You know, you should think like R equals Z or Q or Z sub M, something like that, right? In your head, you should just imagine those are like examples of rings that we have, like the integers, the rationals, the mod, these mod rings. So definition, let A be in R. We say A is a unit. I'll call it U. We say U is a unit if and only if it has a multiplicative inverse. If and only if there exists an X in R such that UX equals 1. So the units are the numbers that have multiplicative inverses within the same set. right? I can write that down. They claim these are going to be useful here. Well, we just get these definitions on the board, and then we can sort of point at the tables now that we have mods 5 through 11 on the board. So, i.e., a unit is an element with a multiplicative inverse. So for example, in the integers, which integers have multiplicative inverses? Which integers can I pick to satisfy the equation ux equals 1? Only a couple. Does any integer have a multiplicative inverse? What's an integer? Not 2, not 3, not 4, not 5, not 6. What integers do have multiplicative inverses? 1. 1 times 1 is 1. And what's the other one? Who said it? -1. -1 times -1 is 1. So plus or minus 1 are units. And in fact, those are the only ones. We haven't proved that. We can prove it. It turns out it's not that hard to prove. But well, actually, you have to prove something on the test that would be helpful in proving. Yeah. And these are the only units. What about like in Z5? We still have 1 times 1 equals 1. What else is a unit? What else has a multiplicative inverse? What else has something you can multiply by to get 1? Yeah, like, look, 2 times 3 is 1, so that makes both of those units, right? What about 4? Does 4 have a multiplicative inverse? 4 times something equal 1? Yeah, 4 times 4, right? 4 times 4 is 1. So all non-zero elements. So all of 1, 2, 3, and 4. All non-zero elements have a multiplicative inverse. 0 is never going to have a multiplicative inverse, right? Are units. Or I'll just say have a multiplicative inverse. What about mod 6? Which ones have multiplicative inverses? 1 always has a multiplicative. 1 times 1 is 1. What else has a multiplicative inverse? Yeah. 5. 5 times 5 is 1. In Z6, just 1 and 5. In Z7, if you look on the board over there. What am I really looking for? Like, look at 7 versus 8. What am I really looking for if I want to say it has a multiplicative inverse? Yeah. What's that? Sorry? Oh, like something to do with if it's a prime mod or not. But I'm just in general, like, how do I know? Like, I claim 3 is a unit in mod 7. Why is that true? Because there's a 1 in the row. Exactly. 3 times 5 is 1. Turn the camera over to watch me. But 3 times 5 is 1 mod 7. So 3 is a unit. So what are the units mod 7? I everything's a unit, right? Everything has a multiplicative inverse. Over here, mod 8, 1, but not 2, 4, 6, right? So if you look at the tables, so in Z7, 1, 2, 3, 4, 5, 6, again, it's all non-zero elements. All non-zero elements. In Z8, it's just 1, 3, 5, and 7. What about in Z9? Erase my tables. I know these are not that. I guess we can just look at the 7 through 11 tables. No. In Z9, what are the units? Which rows have ones in them? Yes.
1, 2, 4, 5, 7.
Yeah, do you guys agree with that? 1, 2, 4, 5, 7, 8. 3 and 6 don't have. Z9. 1, 2, 4, 5, 7, 8. Yeah, well, we might as well finish this, right? In Z10. Those rows that have ones are 1, 3, 7, and 9. Those are the rows that had all the numbers in them, right? 1, 3, 7, 9. And in Z11, it was everything, right? It was all non-zero. Okay, we'll talk about what this means in a moment. You might see the pattern of like which things are units, which aren't. But let me give you another definition. Let X in R in a ring be non-zero. So I don't want 0. We say X is a 0 divisor. This is another term, 0 divisor. If and only if there exists Y in R, Y not equal to 0, such that X times Y equals 0. So two things that are non-zero to multiply to 0 are called 0 divisors, right? Basically, they're things that go divide. I don't know. It's a kind of an archaic terminology, 0 divisor, but that's what people called it. So these are non-zero, i.e. non-zero elements that multiply to 0. So in the integers, there aren't any, right? There are no 0 divisors in the integers. If A is not 0, then there's no way to make A times B equal to 0, right? In Z5, there weren't any, I think. We saw there weren't any. Let's just like make some of these lists again. In Z5, none. In Z6, which are the 0 divisors in Z6? What's a 0 divisor? Yeah, 2 times 3 is 0, 3 times 2 is 0, 4 times 3 is 0. So erase this now. In Z6, 2 times 3 equals 0, and 3 times 4 equals 0. So 2, 3, and 4 are 0 divisors. What about in Z7? 0 show up in the table anywhere? No. None. In Z8, what are the 0 divisors? You guys seen this? Okay, where we're going with this. 2, 4, and 6 are the zero divisors. So in Z8, it's 2, 4, and 6. In Z9, it's just 3 and 6, right? There's only places zeros appear. Yeah, I guess I should say here, 2 times 4 is 0, and 4 times 6 is 0. In Z9, 3 times 3 is 0. 6 times 3 is 0. So 3 and 6. In Z10, yeah, 2, 4, 5, 6, and 8. 2 times 5 is 0. 4 times 5 is 0. 6 times 5 is 0. And 8 times 5 is 0. So 2, 4, 5, 6, and 8. I should be circling these or something. So 2, 4, and 6. 3 and 6. 2, 4, 6, 8, and 5. What about in Z11? None, right? What do you notice? Yeah. Every non-zero element in these mod rings is either a unit or a zero divisor. It kind of partitions this into two pieces, right? Like here in Z8, we got 2, 4, and 6 as the zero divisors, and 1, 3, 5, and 7 is the units, right? Okay, good. That's a conjecture. Conjectures. It's actually what I do a lot when I teach number theory. Is I just like look at a lot of data and patterns and just try to make conjectures about to find the pattern, you know, write down what the patterns are saying. Oh, okay, I'm gonna erase your beautiful Z9. Sorry, guys. Oh, was I gonna take photos before? Oh, it's on, definitely on video, right? It's been on video a lot. Oh, I left the video up, which is actually super weird. Okay. So conjecture. Conjecture is something that we think is true, but we don't know yet. Every non-zero element of Zm is either a unit or a zero divisor. I guess it's almost like exclusive or, right? One or the other, but not both. Can you identify which ones are the units and which ones are the zero divisors? You're nodding. Oh, you're just nodding for just to be agreeable. Anyone besides Audie see it? I know Audie sees it. Steve, you see it? You see it? Is that what you're going to say? Something like that. It has to do with sharing a common factor, right? Like in mod 10, 2, 4, 5, 6, and 8, all share common factors of 10. And in mod 7, nothing shares a common factor with 7, so everything's a unit, nothing's a zero divisor. So further conjecture are the zero divisors are the numbers that share a common factor with m. And the units are the numbers that share no common factor. That share no common factor with m. There's a word for this. I can't remember if I've said it already, but they're called relatively prime. Like 3 and 8 are relatively prime. They don't share any common factors or coprime. So the terminology is relatively prime or coprime. For no common factors. Okay, so I'll start using that. I mean, I'm going to talk about greatest common divisors at some point. So like another way of saying that the greatest common divisor is 1. I'll write that on the board at some point. But okay, so this is kind of cool, right? Like that everything, there really is a lot of structure in these tables. And we certainly want to prove these at some point. You could maybe prove the zero divisors thing. You can sort of see how you might, if something's not relatively prime to the mod, that you could somehow construct something to multiply it by to get 0. But I do want to just throw some other terminology at you just while we're here, which is, by the way, I should have said in Q, in the rationals, every non-zero element's a unit. Right? Everything has a multiplicative inverse, and it has no zero divisors. In Q, every non-zero number has a multiplicative inverse. But there are no zero divisors. Just like in the integers. And I'll say that if you have a ring, if we have a ring where, because ring axioms, oh here, right, the ring axioms here include additive inverses, but not multiplicative inverses. If you add multiplicative inverses, you get something called a field. And I'm just to throw this terminology at you guys, just to get it in your head. There's a class called rings and fields that you could take later, so you might want to. So if a ring R also has the property that every non-zero element has a multiplicative inverse, it's like another axiom, kind of. You always have to say non-zero, though. Element has multiplicative inverse, then it's called a field. Yeah, there are these 3 big algebraic structures in math: groups, rings, and fields. Groups are somehow simpler but more abstract. Rings and fields are very concrete because they're all the number systems that we're used to. So this is called a field. And so, for example, Q and the rationals, the reals, the complex numbers are all fields. But there's also these finite fields. We've seen Z7 and Z11 are fields. And that's kind of cool. Like, in fact, a lot of people study finite fields to try to figure out what's going on in the infinite fields, which are often much more complicated. So the rationals, the reals, the complex numbers are all fields. They're rings too, but they're really fields. I mean, it's ring plus more. And Z mod 7, Z mod 11. Really, which ones are going to be fields? Mod what? When is this happening that we get no zero divisors and we get all units? Prime mods, right? If you have a non-prime mod, you can definitely get a zero divisor. Like in Z22, 2 will be a zero divisor because 2 times 11 is 0, right? P for any prime P are fields. Okay, so that's kind of neat. But then if anything, yes, if we have a nod prime, it's not a field and it also has 0 divisors. So we'll want to prove this. We still haven't proved that like everything has an inverse. And we will prove it. But not quite yet. Okay, so there's a lot of structure here, right? It's good stuff, right? Okay. Yeah. Okay, so that's all I want to say about mods today. My outline, the modular stuff was like this much, and then I have all of this other stuff I was going to talk about. So we only have 15 minutes left. But so there are other things I want to talk about that are related to all this. One of those things is GCDs, like greatest common divisors. The other one that I would like to start talking about is division. Because we haven't axiomatically shown that we can do division with remainder. And we gave that definition of mods as like if two things have the same remainder when dividing by m. So 15 minutes, can I do all the division stuff? Maybe not. I don't want I kind of need division stuff to do GCD stuff. So let's just talk about division a little bit. So we'll just get started talking about division. So this means with quotient and remainder. Notice axiomatically, we're still not really talking about fractions. We're just talking about the integers still. So I don't want to think about like 7/5. I want to think about like 7 divided by 5 with quotient 1 and remainder 2. So we sort of believe that, right, if we have any two integers, we can divide one by another, get a quotient and remainder. So let me just state that. The statement is, let's just talk about it for natural numbers. So if I just take two natural numbers and I want to divide A by B, I want to say that there exists a Q and an R, which are going to be my quotient and remainder integers, such that A equals BQ plus R, right? That's what it means to divide and get a quotient and remainder. And R is in a specific range, right? R is less than what we divided by and greater than or equal to 0. That's the statement of division, right? E.g., like just A is 32, B is 7, right? Actually, I just had the same quotient remainder. Let me do 33 and 7. A is 33 and B is 7. Then you do 7 times 4 plus 5. And so this is your Q, and this is your R, and R is less than 7, greater than or equal to 0, right? You can always find a remainder. In fact, this is sort of saying that reducing mod m is a well-defined operation. Like we can always write each number. We can always find a remainder between 0 and what we divided by. I guess I could put 5 here. Looks kind of silly. Yes, 0 is less than or equal to 5. But I'm just illustrating the statement, right? So that's the statement of division. The real question is how you would prove it. And you can prove it from axioms. And the thing is, I should have thought about it for a little bit, and I realized you could sort of prove it with weak induction, with strong induction, or with the well-ordered principle. So maybe today I'll just kind of sketch the weak and strong induction arguments. And then I like the well-ordered principle argument more because I'm weird. And I'll talk about that. I'll start class with that on Thursday. But let's just do the weak and strong. I mean, I'm not going to write them out like super precisely. I just want to sketch them out. Like, how would you prove this by induction, right? It's already a little bit weird because we have like two unknowns, A and B. We don't just have like an N. So you do have to think about this a little bit carefully. But so proofs. So weak induction argument. So that's when I want to go from one case to the next, right? Like from K to K plus 1. And the idea for the idea for the two induction arguments is you're going to fix B and induct on A. Like just pretend that B is like a fixed number, and we just want to prove that we can do every A can be divided by B to get a quotient remainder. So fix B, induct on A. Again, I'm not writing out the full formal proof, but the base case, when A is 1, what's my quotient and remainder when A is 1? And I divide by B. Jump in on everything, which is great, but I want to give other people what's like. If I just put A as 1 and take a B up there, what's my quotient going to be when I divide? And B is 10. What's your quotient and remainder? Yeah, just 0, and Q is 0, and R is 1, right? Take Q equals 0, R equals 1. So 1 is B times 0 plus B, and 1 is less than B. I guess we're thinking of B and being at least 1. By the way, you can't divide by 0. B should not be 0. I'm saying A and B are natural numbers to make things a little bit easier. A and B could be any integer if you want, and still you can do this, except B shouldn't be 0. Okay, so that's the base case. And you could do it for 2. But the inductive step, so you assume it's true for A equals K. Assume true for A equals K. But that means that sort of K equals BQ plus R, right? So what happens when you add 1? There's a couple cases to think about. Yeah. Yeah, you can think about that with an example, right? Like that. What do we do? 33 and 7. Like 33 is 7 times 4 plus 5. So if you go up 1 to 34, what do? You're saying you just add 1 to the remainder, right? 7 times 4 plus 6, and then you go from 34 to 35. Well, now if you add 1 to the remainder, it's too big. But you get a 7, so you can make that, so this you increment the remainder by 1. Here you can increment the quotient by 1, and then set the remainder back to 0. Does that make sense? Yeah, so basically exactly what you said. So for A equals K, for K plus 1, add 1 to the remainder, add 1 to R if R is less than B minus 1, I guess. And add 1 to Q, or set R equals 0 and add 1 to Q. Q if R equals B minus 1. Make sense? So you could sort of imagine doing that, like just inducting, like you can sort of step your way up, step by step. So that's definitely possible to do that. Any questions about the weak induction argument? Usually illustrating with numbers usually makes it more clear. Okay, now let's just give the strong induction. I just sort of thought about this, like you could also do this with strong induction. And again, you would fix B and induct on A. For the base cases, I might want to, I guess what I want to say is like everything from 1 up to B, everything from A equals 1 up to A equals B, you could just write down explicitly. For A equals 1, 2, 3 up to B minus 1, just write A is B times 0 plus A. Right? That's kind of what we do with 1. Just take Q equals 0 and R equals A. And I want to do for A equals B also, A equals B times 1 plus 0. So I could do everything up to B, just like explicitly, right? And then, so we can assume now that A is greater than B. We're fixing B and then inducting on A. So B is some fixed number, and then we want to like let A be as large as we want. And then the inductive step is, assume division works for all A less than or equal to K, right? So it's a specific K. And then for K minus 1, or K plus 1, sometimes when you do strong division, you do up to K minus 1 and then you do the K case. It's like, it doesn't really matter. You either do K to K plus 1 or you can do K minus 1 to K. And for some reason here, I just want to do it like that. And then for A equals K, and we know A is greater than B, right? So for A equals K, use the K, basically subtract B. Right here, it's like if we know, let's say we know everything up to like, let's say we know everything up to 32. Then if I want to do 33, I could actually look at 26, 33 minus 7. Right, so like, or maybe I want to do 40. Let's say we know up to 39. Maybe that's just easier. 7 times 5 plus 4. So for 40, look at 40 minus 7. Right? What's the difference? What's going to be the difference in the division argument for 40 versus 40 minus 7? When we divide by 7. What's the difference between Q and R? You get where I'm going with this? Steve?
Q will be 1 higher.
Yeah, between 40 and 40 minus 7. Like 40 is going to be 7 times 5 plus 5. 33, 40 minus 7 is 7 times 4 plus 5. So if we write K minus B, which is less than K, right? Use that case. So K minus B is BQ plus R. And then we can just add the B over to their side. K equals B times Q plus 1. Right, so basically we're just going to go back, we're just going to step back to the case where we subtract B, write down the quotient, write down the division for that, and then just add the B, just adds 1 to the quotient, right? So that's when you're not using the previous case, you're using like a specific case before, but not the previous case. Bless you. K minus B case or something like that. Right. Does that make sense? I'm just trying to sketch this. I'm not trying to write it out as a nice formal proof. This is a way to think about it. So that, yeah, so you could do it as a weak induction. You just either increment the remainder or set the remainder back to 0 and increment the Q. Or you can do it as a strong induction just by incrementing the Q. You're almost doing all the cases like, it's like I'd be doing 29 through 35. From 29 through 35, I can, or 28 through 34, I could get up to 35 through 41 just by adding 7 to all those and adding 1 to the quotient. Makes some sense. Okay, good. So then Thursday I will do the proof, the well-ordering proof, which I like more. And we'll talk about GCDs a little bit. And there's still a few things from the set chapter I want to finish up before we move on to the functions and maps stuff. Like I said, I'm just peppering in the number theory stuff because I like it and it's axiomatic. It'll be useful. All right. Well done. If you don't mind erasing your boards, I know you guys did beautiful work, but at least I got it on film.